Hello students, in this video we'll consider the Riemann problem for the Burgers equations. So traditionally in scalar conservation laws there's a classical Riemann problem. And we'll do it in this case for Burgers equation. Remember what Burgers equation is, it's ut plus u dot ux is equal to 0. And this of course can also be written in the following way as our conservation law as a 1/2 u squared and then x equals 0 like that. That's another equally valid way of writing the Burgers equation, so it tells you how this thing scales. And so in particular what this allows us to do is we're going to consider special initial data. So here's a special class of initial data for this problem. You're just going to look at what? You're going to look at functions that have a jump, right? So in other words, you're going to look at 5x as your initial data. This is going to be your u of x and 0. And it's going to be equal to ul if x is less than 0, and it's going to be equal to ur if x is greater than 0. I'm assuming here that ul is less than ur, or that's the important assumption. Ul is less than ur. If this is the situation over here, we're not going to get a shock, we're going to get a rarefaction wave. So ul less than ur implies that there's a rarefaction wave. And no shock. Okay, let's see, why is that the case? Well, it's easy to see. How so? I know that the solution to Burgers, u of xt, implicitly is phi of what? Is phi of x minus t u of x and t, right? In other words, u is constant along these straight line trajectories, right? So in particular, when t is equal to 0, what can you say? When t is equal to 0 and x is less than 0, so if x is less than 0 and t is equal to 0, then what you have? Then the line over here is going to give you what? The line over here is going to be x minus t ul, right? Equals a constant c1. If x is greater than 0, when we plug in t equals 0, what do we see? We see that the solutions look, the characteristics are x minus t ur is equal to c2. So these are our characteristics, right? These are our characteristics of the curve. And we want to make sure the characteristics and we want to make sure those characteristic curves don't cross over here, right? Well, of course, what's the slope of these things over here? The slope of these things, t is a function of x. Well, this first equation over here tells you what? You can either have what? You can either have x minus c1 is equal to t ul, right? Which is the same thing as what? Which is the same thing as t is equal to x minus c1 over ul, right? The second set of trajectories is x minus c2 is equal to t ur, right? And that says that t is equal to what? Is equal to x minus what? c2 over ur, right? Now, of course, what's the slope? The slope of, since ur is bigger than ul, I know that 1 over ul is bigger than 1 over ur, right? So those slopes over there are bigger, right? Which means over here that you're going to have this fan sort of shape. So in other words, these are bigger slopes and those are smaller slopes, right? So the smaller slopes are on the right, the bigger slopes are on the left. So there's going to be necessarily a fan, right? So let's think about what the situation looks like over here. So if we have our x-axis over here and our t-axis over here, we have very small slopes over here, like this, small slopes. And over here we have very large slopes, right? Like that. So let me draw this a little bit better. Let's redo that so make the picture clear. Change up the color. Here's the x-axis, here's the t-axis. Okay, when x is positive, the slopes are very small. And we know what u is equal to on those slopes. We know that u is equal to ur in this region over here, right? And then when you're negative, you have larger slopes, right? So what do the larger slopes look like? Or they could be negative too, right? Like that. And on those larger slopes, you have u is equal to ul, right? Now, of course, there is this region over here where I do not know the solution, right? So this region over here, omega, The solution is unknown. So what's our scheme by which we define the solution in that region omega? Well, what do we know? We look for solutions that are self-similar of the form phi of x of t is my function of v of xt. And we've seen this in previous videos that when you plug this into Burger's equation, you see that v solves Burger's if phi of x is equal to x, right? In other words, phi, so in other words, v of x t is just going to be what? It's just going to be a stream of curves that look like x over t. Solves Burger's. Okay. Excellent. So now we can define our solution, right? I can define our refraction wave. I can have a continuous stream. So of course the slope of this line over here is what? The slope of this line in the negative range is going to be 1 over, these slopes are 1 over UL. These slopes over here are 1 over UR for these lines over here. So in other words, when x over t is between those two values, right? So when x over t, that's, and of course, the slope of this line over here. So if x over t, if we set x over t to be equal to lambda, then what does that say? That says that x over lambda is equal to t, right? And so, of course, what's happening over here to lambda? So lambda is going everywhere between 1 over UL and 1 over UR. So what do we know about x over t? So this lambda over here is going everywhere between UL and UR, right? So if that lambda goes between UL and UR, I have a continuous family of functions, right? And so what it allows me to do is write down the solution now. So I can write down our solution to Burger's, which is going to be what? The solution to the Riemann problem. U of x of t is going to be what? Well, it's going to be UL provided what? Provided x over t is less than what? Is less than UL, right? It's going to be x over t, and it's going to be UR provided x over t is bigger than UR. UR. And finally, it's going to be x over t in the intermediate range. UL less than x over t less than UR. And this is a continuous weak solution. This is a continuous weak solution of Burger's equation. Okay. And so what we've done over here is we've solved Burger's equation just by simply allowing me to do what? Make this rarefaction fan in between this region omega and bridge the solution from these UL values to these UR values. So what we're doing over here is in some sense we're building a ramp, right? I have the UL values, which are less than UR, building a ramp up to the what? Building a ramp up to those UR values. So that ramp over there, so what's happening? If you think of this from the calculus perspective, if we gave you a function in calculus that looked like this, if I said, here's a function, you'd say that's a nice fine continuous function, it's a nice fine ramp, I'm stratifying the slopes. But what's the issue over here? The issue over here is not differentiable at those 2 points where the ramp starts and where the ramp ends. So of course this is not a differentiable, it's not a classical solution to the Burger's equation, but it's a continuous weak solution to the Burger's equation. And for our purposes that's satisfactory because it comes from the conservation law, it comes from a physical problem, therefore a continuous solution is good enough for us. Thank you very much.